Hello everyone! Today we'll be talking about the quantum Fourier transform and how it can be used to find the period of a function. To start, we have a function of time f of t, and we want to write it as a linear combination of sinusoidal functions. Nu represents frequency, and since we're considering all frequencies, we have an integral as opposed to a sum. F tilde nu is called the Fourier transform, which is actually related to f of t by this integral. We're interested in the Fourier transform because it gives us information about f of t, such as its period and rate of decay. Today, we will focus on the period of f of t. What happens if the function f is not continuous, but is given by a discrete set of n points equally spaced in time by delta t? How can we find its period? First, we need to define its Fourier transform as given by this expression, where the L in the n-term sum is an integer that replaces the nu we saw previously. This is called the discrete Fourier transform. Next, let's look at an example to show how the period can be found using it. We will consider a periodic function, which is period 2, so r equals 2, and the sample size is 6. Writing out the discrete Fourier transform gives this, and since r equals 2, the values of f alternate between f0 and f1. After some algebra, we find that the expression can be written this way, where eta is given in the upper right corner. This sum can be written using this geometric series formula this way. Let's focus on the absolute value of this quotient. For all L, eta to the 6 is 1, which means that the numerator is always 0. Eta squared, however, is 1 only for L being 0 or a multiple of 3, meaning for these L values, the denominator is 0. So we have situations in which that absolute value equals 0 over 0. That's not good, but L'Hopital's rule saves us. And when we take the limit L goes to 0, that expression equals 3. Which is the number of complete periods in the n equals 6 sample. If we label that q and use the fact that n equals 6, then n divided by q equals 2, and that gives us the period. How can we use quantum power to make things better? Well, quantum power comes in the evaluation of the values of the function f from f0 to fn minus 1, n equals 6 here, in one single step, as opposed to doing that n times in the classical case. So, in order to take full advantage of the power that quantum parallelism offers, we need to know how to define the quantum analog of the Fourier transform. Well, the quantum Fourier transform is the quantum analog of the discrete Fourier transform, as you can see here. F tilde L is replaced by ket L and Fk by ket K. Notice that there are 2 to the L terms on the right-hand side, where uppercase L is the number of qubits. To obtain this expression, you apply the quantum Fourier transform only once on ket L. Also, notice that in this equation, the numbers inside the kets are in base 10. So, in situations when you expand it and work it out, make sure to convert the numbers to binary to make the states of the qubits clearer. The next question is, how can we implement the quantum Fourier transform gate, i.e., what combinations of gates take ket L to what you see here on the right side of the equation? Let's look at how it can be implemented for 2 qubits. To find the binary representation of the L in ket L, we need to decompose it this way to get L1, L0 as the representation. Then we input the 2 qubits which represent them into this quantum circuit. The state starts as ket L1, L0. A Hadamard is then applied on the upper qubit, followed by a controlled phase gate, then a Hadamard on the lower qubit, and finally the swap gate is applied on the 2 qubits to obtain the Fourier transform here. This can be extended to a general L-qubit state, where the quantum circuit to achieve that looks like this. Now that we know how to implement UQFT, we can use it in the following way in this generic quantum algorithm with the multiple Hadamards and the function evaluation unitary to find the period of function f. Note that just before the measurement at the end of the circuit over here, the measurement outcome for the argument register is at a high probability of being s times 2 to the L over r, where s is an integer between 0 and r minus 1. Since we know L, we can factor 2 to the L out, then we will be left with s over r. We need to know what s is exactly before we factor that out to reveal the value of the period r. Since s could be one of r possibilities, we repeat this experiment several times to find out multiples of what we're looking at to finally reveal r. This is like how Millikan determined what the charge of the electron is in his oil experiment. He found that all the negative charges in the experiment were whole number multiples of the same negative charge. As an exercise, go back to the quantum Fourier transform circuit for 2 qubits and work out the 3 intermediate middle states. Martian late,